we're going to take another look at elimination substitution reactions. So here we have our substrate and our reaction reagents and our reaction conditions. Now, the first step of our strategy is to identify the location of our leaving group on our substrate. So here in this example, we have iodide is going to be our leaving group. It's located on a secondary carbon, making this a secondary alkyl halide. Go ahead and write that down. Because we know that secondary alkyl halides prefer either SN2 or E2 mechanisms, we can go ahead and select those two options now. To be able to determine most likely between those two, we would go to our second step of our strategy, which would be to identify characteristics of our reagents. So coming over here, we see that we have sodium ethoxide and ethanol, and we have a reaction condition at 70 degrees Celsius. So how do you determine between the sodium ethoxide or the ethanol, which of these two will be our acting reagent? The trick to this is to go ahead and place your electron pairs on your atoms along with any overall charges. On the sodium ethoxide, we can see that we have an overall negative charge, and we have a positive on the sodium, which will act as a spectator. Down here on the ethanol, we can see that we've got electron pairs but no overall charge. So between these two, the sodium ethoxide is going to be the stronger between the two, and it's going to be your acting reagent. Now, because sodium ethoxide is a good base and a good nucleophile, we need to consider our other reaction conditions. We have a secondary alkyl halide. We also have a temperature at 70 degrees. Given all of these factors, we can most likely predict that the mechanism that this will proceed through is going to be an E2. Now, because we have a secondary substrate, there are two possible locations that a double bond can occur. Now, the first thing, the negative charge from the oxygen can abstract the hydrogen on this carbon, which would lead to double bond formation between these two carbons. The other possibility is that the negative charge will abstract a hydrogen from this location, this ethanol, this methyl group, and create a double bond formation between these two carbons. Because sodium ethoxide is both a small, unhindered, and strong base, then Zaitsev product is going to be the one that's going to prevail, leading to most stable alkene, which would be double bond formation here. Stereochemistry is something that we need to consider with E2 reactions, and we can do this by looking at interconverting the molecule to Dash wedge formula and Newman projection. E2 reactions are very stereospecific. They require the iodine and hydrogen to be in the anti-conformation in order for the reaction to occur and the double bond to take place. So here we have the model of the formula, and we have the iodide in blue, and we've highlighted the hydrogen that's going to be abstracted in red. And you can see in the Fischer projection that these atoms, that this molecule is, the atoms are eclipsed in this conformation. So we can redraw them in Dash and wedge structure and also Newman projection in order to help get it in an anti-position in order for the reaction to take place. So in order to do this, we'll use our molecule. And you can see, we'll go ahead and just draw this in. We have the iodide here, and we have the hydrogen here, and we have a methyl group here in the back, and we have that displayed here. Keeping everything the same, here we have the hydrogen atom. Back behind it, we have an ethyl group going to the back. I'm sorry, the ethyl group going to the back. And then in the front, we have our ethyl group. Now just turning this so that you can see it down the front in the Newman projection. Again, we have our iodide group here in the front, Eclipsed behind it is the hydrogen group. And then over on the next molecule, we have a hydrogen here in the front. Eclipsed behind it is the ethyl group. Sorry, methyl group. In the front, we have a methyl group, and directly eclipsed behind it, we have the ethyl group. Now, in order to get this in the anti position, all we need to do is rotate about the bond in between these two carbons 180 degrees. That'll put the hydrogen and the iodide in an anti-conformation in order for the reaction to take place. So doing that, rotating that bond, again you can see using our model, we have the iodide at the top, and now we have that hydrogen in the anti-position where we want it. And we have now our ethyl group is coming out towards the front. And our methyl group is going towards the back. If we look at this again, in the Newman projection, you can see that we've got iodide on the front. The hydrogen is going to be in the Newman position. I mean in the anti-position. Now, at the top, you have the methyl group. In the anti-position to it, you have the ethyl group. That's an H, sorry. And then you have the hydrogen in the front here, and in the anti-position to it, you've got a methyl group. Now with these being in the anti-position, now it's ready for the reaction to proceed, and the base can abstract the hydrogen as the iodide leaves, creating the double bond. And we can take a look at this reaction further. Okay, now that the iodide and hydrogen are in an anti-formation, now we can go ahead and work the reaction. The electrons from the base come up here and abstract the hydrogen. We can go ahead and follow the electron flow throughout the reaction. Iodide leaves, causing double bond formation to occur between these two carbons here. Once this happens, the carbons go from sp3 hybridization to sp2 hybridization, causing the overall molecule to be flat. These groups here come up, and these groups here come down. This results in our product being planar overall, which is right here. So here, I'll draw these groups in. You can see the same thing occur in our Newman projection. Once the hydrogen and iodide groups leave, methyl group comes up, hydrogen group comes down. And we can draw that in our new Newman projection. Both the Newman projection and the Dachau wedge now represent our major product that has formed. And if you'll remember back to the substrate that we started with, it was the secondary alkyl halide with our iodide being right here. And as we mentioned, there was the possibility of two locations for the double bond to occur. We have the major formation, which was what we've just shown, but we also had the possibility that a double bond could form here. That's represented down here in our minor product. And you can see from our major product that's formed the overall flatness of the molecule and the planar geometry of it. And that is the E2 reaction.